All right, I'm not sure why this section is so far into the chapter on gases, but we're going to go ahead and talk about kinetic molecular theory right now, and we'll get a little bit more into ideal versus real gases. These postulates are based on all the different experiments that have led to us developing knowledge about gases, that their individual particles are so small that their volumes are negligible individually, that we'd look at them as taking up whatever space is available in their container, that they are in constant, random, and rapid motion, and that their pressure is developed by the number of collisions that they form with their container walls as well as one another. They do not attract nor do they repel one another, and that their kinetic energy is directly proportional to their Kelvin temperature, and that if you are at a given temperature, all gases should have the same average kinetic energy. So the relationship between kinetic energy and temperature has been determined using your kinetic energy 1/2 equals mv squared. And we have also been able to relate our energy in the form of temperature um, with measurements that we would take in chemistry class. And so when we take those two and put them together, we get that kinetic energy is equal to 3/2 R times T. So it's a index of the random motion of your gas molecules, greater temperature, more motion. And so we use the constant in joules to be able to calculate this, 8.314 joules per mole Kelvin. And again, your temperatures have to be in Kelvin. So if I wanted to find the velocity of, or the average velocity of my molecules, I could take that kinetic energy equation, 1/2 mv squared, and I could set it equal to the 3/2 RT. And when I put those together, I can solve for what velocity is equal to, which is the square root of 3 times the constant that's in joules times your Kelvin temperature over your molar mass. But your molar mass, because your constant is in joules, needs to be in kilograms so that the units will cancel. We talked briefly about this before. Real gases do not conform to that kinetic molecular theory because they have individual volumes and they are able to exert pressure on one another. So we have to correct ideal gas behavior when we are at higher pressures due to that smaller volume and at lower temperatures due to the attractive forces that start to come. So here we're going to calculate the average kinetic energy of N2 at 323 Kelvin. So we just use that relationship between kinetic energy and temperature. We substitute in what we know, our constant, our Kelvin temperature, and that 3/2. The kelvins cancel out, and we're left with a kinetic energy equal to 4,030 joules per mole. We can also use that relationship to examine root mean squared velocity. So with root mean squared velocity, we know our constant, we know our temperature, and remember with the molar mass, oxygen would be 32 grams per mole, but because joules is in kilograms, we needed to convert our grams into kilograms, dividing it by 1,000, 0.032. The moles and the kelvins cancel out. Joules is 1 kilogram, 1 joule is equal to 1 kilogram meters squared per second squared. So the kilograms cancel, and when you take the square root of meters squared over second squared, you get meters per second. So that would be 502 when you do this calculation. And then the final question we're going to look at in this section, you have 1 liter samples of hydrogen, xenon, chloron, and oxygen. They're all at constant pressure. How could each of these gases have the same average velocity? If they are all at the same pressure and we want them to have the same velocity, we would have to have a ratio of your Kelvin temperature to their molar mass that would be the same because the other two values are constants. So I don't necessarily expect that you write everything down here that I have as an answer, but you will notice that typically when you have a lighter gas, you would need a lower temperature, and when you have a heavier gas, you would need a greater temperature if you want those ratios to be equivalent.